Hello, this is Lazarus at Telecom Tech, where telecom and networking technologies are simply explained. Today we'll be simply explaining an OSPF basic configuration on Cisco IOS routers. I'll say it all very quickly so I won't tire you out. Check out my website at telecomtech.io, where you can check out blog posts on topics covered on the YouTube channel, and you can register for my newsletter, where you'll get information of new content. And coming very soon, in-depth courses with labs, configurations, quizzes, practice exams, and downloadable content in PDF format. Now that that's out of the way, let's get started with our OSPF configuration. Now, in order to understand how OSPF works, let's take a look at the way a Cisco IOS router behaves when we configure various components of the OSPF configuration. Take a look at this simple topology with two OSPF routers. In this video, we'll enable OSPF on both routers, we'll enable OSPF on these particular interfaces, and then cause the routers to become OSPF neighbors. We'll also configure one of these two networks here to be advertised through OSPF to the neighboring router. The first step here is to enable OSPF on R1. To do this, we use the following configuration in global configuration mode. We use the command router OSPF1. Now, this command enables OSPF on the Cisco IOS router. The router part of the command is used to enable routing protocols on the device, and the OSPF keyword tells the router what routing protocol is to be enabled. The designation of 1 here is used internally by the router to identify the OSPF process that we are configuring. The number can actually be anything, and it's not related to the process ID configured on other OSPF routers. The number is only locally significant. Now note here that the purpose of the process number is to allow us to run multiple instances of OSPF on the same device. Now what does that mean? Well, this router is able to participate in more than one OSPF domain. You can configure multiple independent OSPF processes and then have different networks participate with different OSPF processes. This is especially useful in MPLS implementations with multiple VRFs, for example. If you're not sure what I'm talking about, not to worry, this is beyond the scope of this video. So now OSPF is running on this device, and it's just that one command that enables it. But no networks are yet being advertised. Let's advertise our first network. To do so, we issue the network command like so. Now, what does this command tell us? We're essentially saying to the router that any directly connected interface that falls within this IP address range should participate in the OSPF process. Now, OSPF typically requires us to use the wildcard mask to specify the IP address range. In this case, the network with the wildcard mask is the same as the network that is configured on interface Gigabit Ethernet 01. Now, this has several results. First, this directly connected network is injected into the OSPF database. Second, the interface associated with that network is now participating in OSPF. This means that OSPF multicast messages have started being sent out of this interface, attempting to find an OSPF neighbor on the other end of this link. At this point, there's no answer to these messages, but periodically OSPF messages are sent out. Third, when a neighbor adjacency is created, this network here will be included in the updates that are shared with the neighboring router. In other words, this network is being advertised by OSPF. Now, this last part of the command, the area 0, indicates that this network belongs to OSPF area 0, or to the backbone area. Remember, OSPF has a hierarchical design where you can create multiple areas. This particular network and its associated interface is configured to be part of area 0. Now, every OSPF domain must have an area 0. You can't define a non-zero area on any interfaces or any networks unless you have first established an area 0 somewhere on the network. In a later video, we'll see how to configure multi-area OSPF, but for now, we're going to stick with a single area, the backbone area. So now we have our 192.168.1.0/24 network participating in OSPF, And we have the interface that is configured with an IP address within this range, actively participating in OSPF, thus it's sending out OSPF messages trying to establish an adjacency. Let's now configure the corresponding OSPF configuration on R2. So we start with the OSPF process with this command once again, and we use a process ID of 1. We then use the same command to tell the router that this network and all interfaces with IP addresses within that range will participate in OSPF. This results in the Gigabit Ethernet 01 interface of R2 starting to send out multicast OSPF messages to attempt to establish an adjacency. Now at this point, these two routers should become OSPF neighbors. Let's check that out. We see several things here as the output to this command. I won't explain them all in detail as these will be examined further in future videos. But I will say that you can see that a neighbor adjacency has been established with the router that has a router ID of 20.20.20.1, which is actually the IP address of the Loopback 0 interface of R2. Now the neighbor adjacency is in the full state, which means that the OSPF adjacency has been fully established. You can also see the priority of this router, which is by default set to 1. This value is used in the DR/BDR election. We can see also that this router has been elected as the backup designated router, or the BDR, in this network segment. And we can also see the IP address of the neighboring router through which the adjacency has been formed, which is the address of the Gigabit Ethernet 01 interface of R2. And we see that the local interface through which the neighbor adjacency has been established here is Gigabit Ethernet 01. Now, if we look at the OSPF neighbors established on R2, we see something similar. We see the router ID of R1, which is the IP address of the Loopback 0 interface of R1, and we see a full state for the adjacency, we see the default priority of 1, and we see that this router is elected as the DR, which makes sense, since the other router was the BDR. If you're not familiar with the DR/BDR elections, don't worry, we'll go over those in a future video. And like before, we can see the IP address of the remote interface of R1 through which the adjacency has taken place, as well as the local interface through which the neighborship has been formed. So OSPF has been established. But what have we really accomplished? Let's take a look at the routing table of R1. Now, that's very interesting. There are no OSPF routes. We only see the directly connected networks. And actually, this is expected. Remember, we've injected the 192.168.1.0/24 network into OSPF. But this network is also directly connected to this router. So based on the administrative distance of a directly connected network compared to that of OSPF networks, the directly connected network is preferred and is installed in the routing table. So even though that one network is advertised, the directly connected network is preferred. If we look at the routing table of R2, we'd see the same thing for the same reasons. Now, to see something substantial concerning OSPF, let's advertise the Loopback 0 interface of R1 into OSPF. We can do that using this command. Now, since the IP address and subnet mask of the Loopback 0 interface is within the range of the command, this network is now injected into OSPF. It should now also be advertised to all OSPF neighbors, namely R2. Since R1 and R2 are OSPF neighbors, and since we've specified that we want to advertise this network using the network command, R1 should now have informed R2 of this network. Let's take a look at the routing table of R2. So in the routing table, you can see the OSPF entry here for the 10.10.10.0/24 network. We can see that this destination can be reached via the next hop IP address of the Gigabit Ethernet 01 interface of R1. And we can see that the exit interface from R2 is the Gigabit Ethernet 01 interface. So R2 has now learned how to reach the 10.10.10.0/24 network via OSPF. Now let's check if we have connectivity. Here we see that we can now ping the 10.10.10.1 destination from R2. Thus, OSPF has been successfully used to advertise this network from R1 to R2, and we have successfully established connectivity. So that's the basic configuration of OSPF on these two routers. Well, I hope you found this video useful, and if you have, please click the thumbs up button. Please check out my website and subscribe to my newsletter. You'll find the links in the description below. And don't forget to subscribe to the channel to get updates of newly published videos. I'm Lazarus at Telecom Tech. I hope this has been helpful for you, and I'd like to thank you for watching.